Okay, so we're ready to actually calculate our confidence intervals. We've kind of laid the foundation in class. So there are two intervals that we're going to calculate. We're going to calculate a one sample Z interval for the mean, for the true population mean. We're going to use this one when sigma is known, when you know the true population standard deviation, which should be almost never, right? We don't really know that thing, so we really shouldn't be calculating this one quite that really at all. However, if a problem sets up and says that you know sigma, I guess that's the one to use. The one we're going to use most of the time is a one sample T interval. We're going to use that new T curve that we learned, and we're going to use that when sigma is unknown. So the formula is the same. Remember, confidence intervals are always your stat plus or minus your crit value times, well, overall, plus or minus your margin of error, right? Which is your stat plus or minus your crit value times the standard deviation of the stat. Okay? So in this case, our statistic is X bar, our sample mean. Our crit value is going to be a Z crit if we know the standard deviation. It's going to be a T crit if we don't know the population standard deviation. And then the standard deviation of the statistic is the sigma over square root of n. Or in this case, if we're using our sample standard deviation to estimate it, we use the standard error, which is S over square root of n. That's really it. Okay? So we're going to run these panics like a panic, just like we did on the other one, where we identify the parameter, the assumptions, name the test, calculate the interval, and draw the conclusion. Example. Milk's favorite cookie. For their second semester project in AP Stats, Ann and Tori wanted to estimate the average weight of an Oreo cookie to determine if the average weight was less than advertised. They selected a random sample of 36 cookies and found the weight of each cookie in grams. The mean was that many grams, and the sample standard deviation was that. Construct and interpret a 95% confidence interval. All right. So first step, P. In this case, our parameter is mu, the true. So mu is equal to the true population mean weight of an Oreo cookie. Or you could even say of all Oreo cookies. Whatever. A, check the assumptions. Gonna spend some time here. Number one, random. So we're going to check that off, even though, I mean, they said they took a random sample, but of course they probably didn't. They're probably lying to us, but that's okay. They claimed the sample was random. So they claim the sample is randomly selected. Number two, 10% condition. I'm pretty sure this one passes. N equals 36 is less than 10% of all Oreo cookies. I know this to be true because I have eaten more than 360 Oreo cookies in my life. That's a joke, sorry. Number three, the normal large sample. This is going to check out on this one. Not because the original distribution was normal, not because the sample looks normal, but because I have 36. So n equals 36 is greater than or equal to 30. So the sampling distribution of X bar is approximately normal. By the central limit theorem. And I would say this is the only thing that's really optional on this. The rest kind of needs to be said. I guess actually this is optional. But like this is needed, and this statement here is needed, okay? So try to get that right. Name the test, N. This is a one samp. Now I don't know the true population standard deviation, so this is going to be a T interval for mu. And let's give the formula. Formula is x bar plus or minus T crit times S over square root of N. So now let's actually calculate the interval, I. So my x bar is, 11.3921 plus or minus. Now on these, you have to calculate the T crit on every single problem. Because although it's 95%, it's not going to be that common Z cutoff of 1.96. 0.025. And this is a T distribution with how many degrees of freedom? Actually, and I forgot here, sometimes we say with 35 degrees of freedom. Dang it, normally I put that in here. Degrees of freedom equals 35. At some point, somewhere on your paper, you need to say how many degrees of freedom there are. Remember, it's n minus 1, so the degrees of freedom is 36 minus 1, or 35. So this is a T with 35 degrees of freedom. It's going to be pretty close to the normal, but it's going to be off a little bit. So this should be close to the 1.96, but off a little bit. Inverse T, 0.025 to the left, 35 degrees of freedom, 2.03. So a little bit bigger. So 2.03 for the T crit. And then we're going to put in the 0.0817 divided by the square root of 36. And then type that in your calculator. I'm going to pause it to save some time. Put this in the calculator. There's my mean. There's my T crit. There's my sample standard deviation. And there's my square root of n. So enter. Gives me the lower bound. Just come up and grab that. And minus. I'm sorry, that was the upper bound. And this is the lower bound. So 11.42 to 11.36. So I'm going to go 11.36 to 11.42. 11.36 grams to 11.42 grams. You might say, well, that's, like a really small interval. Well, it has to do with the standard deviation of your sample. And the fact that you're selecting 36 cookies. So we're actually getting a pretty precise estimate for our confidence interval. So, but it is what it is. Conclusion. We are 95% confident that the interval, from 11.36 grams to 11.42 grams captures the, and then you're going to copy down exactly what you wrote up here. The true population mean weight of an Oreo cookie. So what do you need? You need context. You need to say something about weights of Oreo cookies. You need to give me the parameter of interest. You need to say mean or average. And you need to give me an indication that you're referencing the population value, true or population or something along those lines. On the packaging, the stated serving size is 4 cookies, 34 grams. Does this interval in Part A provide convincing evidence that the average weight of Oreo cookies is less than advertised? Well, if they're advertising 34 grams for 3 cookies, 34 divided by 3, that's 11.33. So they're advertising 11.3333. So they're advertising this. However, that is not in our interval. So I would say this does provide convincing, or maybe more precisely, we should say this sample provides convincing evidence. I'm going to say that. I'm going to write that over so it's a little bit better. This sample provides convincing evidence that the weight it actually provides convincing evidence that the weight of cookies is actually more than what's advertised. That the weight is more than what's advertised. So the question says, does the interval provide convincing evidence that the weight of cookies is less? I guess the answer to that question should have been no. My bad. Because it actually provides evidence that it's more. And I guess they're probably doing that so that people don't complain. All right? All right. Just to add, I thought I was going to be able to get both of these examples done in one video, but I'm at 11 minutes, so I'm not going to be able to get it done. If the next example is just another panic, however, this is the check you're going to have to watch out for on the test, okay, this third check. So what's the only thing different about the next one is how this third check is run. So, watch it or don't watch it, I don't care. But I would encourage you to at least watch the section that talks about how the third check is different, all right? So I'll leave it up to you.